Hello guys, in this lesson we're going to be studying the octet rule and oxidation states, how to equalize charges in compounds that are ionic, and also there are some special cases here, those of transition metals and those of polyatomic ions. So there's a homework associated with this lesson. We'll do this in class next time I see you. It's several questions long. And so please write that down as the beginning of your classwork page. And the second thing you should write under classwork is this aim: how do I predict and write chemical formulas? I just corrected some formatting errors, but please copy down these do now questions. Don't answer them, we'll answer them in class next time I see you. Okay, so the octet rule states that all atoms really want to have 8 electrons in their valence shell. And we would use the octet rule to determine oxidation state because as atoms gain electrons to get to 8 or lose electrons to reveal a full valence of 8 underneath their current valence shell, then their charges will change to the negative or even the positive. For instance, all the elements in group 1 have a charge of 1 plus because they all lose 1 electron in their valence shell to reveal a valence of 8 underneath. The group that would have an oxidation state of -3 would be the group that has 5 electrons in its valence shell, which in this case is group 15. So I just tossed my answers in there. Please add those to your notes. So we know that ionic compounds need to have a charge of 0. And opposite oxidation state atoms, or atoms with opposite charges, will bond because of electrostatic attraction. It is not always the case that elements will bond in a 1-to-1 ratio, however. The only rule that is always true is that the ratio must produce an overall sum of charges that is 0, and in the case of an example like magnesium, whose charge is +2, and chlorine, whose charge is -1 in its ionic state, a 1-to-1 ratio would result in a compound that actually had a charge of +1. This is very bad, and it will never happen. So how is it that a magnesium ion and a chloride ion actually combine to equalize charges? Well, they do it in a ratio that is not 1-to-1. And the easiest way that chemistry teachers use to show how this kind of bonding would occur is by crossing charges. So the way you do this is you write down the charge of, or the positive ion, it's always written first, and you write its charge there as superscript. Then you write the negative ion second with its charge as superscript, and then you do something called crossing charges. So the 1 from the chloride ion comes down as a 1 subscript on the magnesium, and the 2 from the charge of the magnesium ion comes down as a subscript of 2 on the chloride. So the formula for a compound containing Mg and Cl would be MgCl2. We never write the 1 as a subscript, so that's why it's blank for magnesium. So let's try an example of a made-up compound like Z2T3. If I want to know the charge of element Z, let's undo what I just have done in the example. Let's take the subscript from T and assume that it's going to be the charge on Z, while also remembering that the charge on Z is always positive because the positive ion is always written first. So the charge of element Z must be Z +3. Let's do a slightly different example, but in this case the compound is ZT4, and that means when you uncross this charge that the charge of Z must be Z +4. That also means that the group that it belongs to must be group 14, and all the elements in group 14, like carbon and silicon, they all have possible oxidation states of +4. Okay guys, I want you to watch this video.
We have learned about how ions are formed and that an ionic bond is the electrostatic attraction between oppositely charged ions. We will now learn about how to name these ionic compounds and deduce their formula from the ionic charges. Let's warm up with a simple example. We know that sodium loses one electron to form a sodium ion. We also know that the electron is not lost, but transferred to a chlorine atom to form a chloride ion. Let's grab a piece of paper and a pencil and work on this example. Write down the ions side by side along with their charges. Remember that the charges are written in superscript. Now, circle the charges and crisscross them, just like how it's done here. We will bring the charges down so that they are in subscript. 1 is never written in a formula. It's assumed that no number written means that there is one atom. So the resulting formula is NaCl. The positive metal ion always comes first in both the formula and the name. For the negative nonmetal ions, the first syllable stays the same, but the ending is dropped and replaced with an "ide." Chlorine becomes chloride. So this ionic compound is called sodium chloride. Let's keep that piece of paper because we will do another example, this time with magnesium and oxygen. Let's write the ions along with their charges side by side. Then we will crisscross these charges. We should get the following formula, Mg2O2. However, 2 to 2 can be reduced to 1 to 1. Therefore, the formula is MgO. The name of this compound is magnesium oxide. Remember that we keep the first syllable and we change the ending to an "ide." Find the formula and the name of the ionic compound formed from calcium and fluorine. Please pause the lesson and resume once you are done to check the answer. The formula is CaF2, with the 2 written in subscript, and the name is calcium fluoride. If we were to think about it, everything we've described makes perfect sense. We know that ionic compounds have an overall neutral charge, so all charges present must be fully balanced. Using your calcium fluoride example, we can see that to fully balance these charges, the calcium 2+ ion must form an ionic bond with 2 fluoride ions. This concept is stitched together when writing its formula, CaF2. We will do one more example together, this time with aluminum and sulfur. The formula is Al2S3 and the name is aluminum sulfide.
I hope that video helped to explain a little bit further why equalizing charges is a really important concept for ionic bonding. All right, so there is some trickier stuff here, and that would involve transition metals, but also polyatomic ions. On this slide, we'll cover transition metals. So all transition metals have something in common, which is that they have more than one valence state that is acceptable. Therefore, we have to always say exactly which oxidation state we're using when we use a transition metal ion, which does mean that you need to be aware of which atoms are in the transition metal area of the table and which atoms are not. For instance, if you weren't aware already, iron is a transition metal, and when we have an iron +2 ion, then we really should be saying this, which involves Roman numerals but would just be spoken as iron 2. If you see the opposite, like if you see tin 3 listed, then that just means this. It means that ion. So let's try an example of crossing charges with transition metals. What's the formula of a compound of iron 3 and oxygen? So let's do this quite normally. You just write the iron 3 because it's positive, so you write it first, right next to oxygen, whose charge is almost always 2-. You cross the charges down, those will become subscripts. So the subscript on the iron is going to be a 2, whereas the subscript on the oxygen will be a 3. Perfect. Let's try another example. What's the formula of a compound of copper 2, which means this, and sulfur, whose charge is almost always -2? Let's cross the charges to get our subscripts. I'm getting Cu2S2. And since ionic compounds form crystals of unlimited size, we don't actually need to have a subscript that is more than the empirical formula. So let's just write the empirical formula, which would be CuS. All right, let's do one more. This is a bit harder. What's the formula of a compound of lead and phosphorus? So you need to pay attention to the fact that lead is a transition metal and has more than one valence state. Therefore, since I did not say exactly what valence state of lead that I meant, this question is impossible to answer. I'm going to give you another video clip from the Fuse School to watch about this topic.
Transition metals are multivalent. This means that they can form ion with many different charges. For example, these copper ions can have either a +1 or +2 charge. If we form an ionic compound from copper 2+ ions and chloride ions, we must specify the valency of the copper ion in its name. So for CuCl2, the name is copper 2 chloride. Note that the valency is written as Roman numerals in round brackets right after the transition metal.
If the ionic compound contains a polyatomic ion, then we also have another complication to deal with. Polyatomic ions are a group of atoms, usually covalently bonded, that have a charge. We can find a listing of them on Table E. One thing you'll notice is that most of the polyatomic ions that you find on Table E are negative ions, which the vocabulary word for that is anion, and the vocabulary word for a positive ion is a cation. So if a polyatomic ion does not bond in a 1-to-1 ratio with another ion, we would need to show this using parentheses. Confused? Let's do an example. Let's do a formula for a compound of copper 2 nitrite. So I wrote down my ion for copper 2, but I need to get the formula for nitrite. Let me check Table E to find out what it is. So I did just check Table E and I found out that its formula is NO2 minus 1. When we want to find the formula for it, we'll need to cross the charges down to find subscripts. And I can see that the subscript for the copper would be a 1, which you never write. But then you write the NO2, and I can see that its subscript is going to be a 2. This is very confusing because I have a 2 subscript right for the whole ion right next to a 2 subscript which applies only to oxygen. So the only way to do this clearly so that you know that there are 2 nitrites rather than, let's say, 22 oxygens, is to put parentheses around the polyatomic ion. This is communicating that there are 2 nitrites needed to balance the charge of 1 copper 2 ion. Let's try another example. What's the formula of lead 2 nitrate? So lead 2 is going to be this particular ion, and nitrate, I'm just checking my Table E right now, and I can see that its formula is NO3 minus 1. We just need to cross the charges to find out what the subscripts will be. The -1 from the nitrate is giving me the subscript for lead, which is going to be 1, which I do not need to write. And the 2 from the lead is going to give me the subscript for nitrate, so I know that I'm going to need a total of 2 nitrate ions. But in order to avoid confusion of thinking perhaps that there are 32 oxygens, instead we need to make it clear that there are really just 2 nitrate ions. So you should include parentheses around the nitrate to show that there are, in fact, 2 nitrates rather than 32 oxygens. Please watch this video from the Fuse School to deepen your understanding.
We have previously learned how to name ionic compounds and deduce their formula from the ionic charges. For all the ions in the examples provided, they have one thing in common. They are made of one atom and are therefore known as monatomic ions. In this lesson, we will learn how to name and deduce the formula of ionic compounds made from polyatomic ions. These polyatomic ions are ions made of more than one atom. Remember that mono means one and poly means many. Some common polyatomic ions include hydroxide, sulfate, nitrate, phosphate, carbonate, and ammonium. Note that with the exception of the ammonium ion, all of the listed polyatomic ions are anions. You will have to remember the formula and the charges of these polyatomic ions. Let's grab a piece of paper and a pencil and work on the first example. Write the sodium ion and nitrate ion side by side. Remember to include their charges. Let's crisscross these charges. Since we never put 1 in a formula, the formula for the ionic compound in question is NaNO3. When naming ionic compounds made from polyatomic ions, we just write their names as they are. The name, therefore, is sodium nitrate. Now, for our second example, let's write a magnesium ion and a hydroxide ion side by side. Let's crisscross these charges. The structure of the hydroxide ion is not changed when forming an ionic compound. For this example, we simply need 2 hydroxide ions to fully balance out the +2 charge of the magnesium ion. This is represented by placing the O and H in round brackets and the 2 as a subscript. So the formula is MgOH in brackets 2, and its name is magnesium hydroxide. Let's say we did not put the OH in brackets. We would get MgOH2. This would mean that for each magnesium ion, there is 1 oxygen atom and 2 hydrogen atoms, which is incorrect. Are you ready to try this on your own now? Find the formula and name the ionic compound formed from potassium and sulfate ions. Please pause the lesson to try this and resume when you are done. The formula is K2SO4 and the name is potassium sulfate. We know that ionic compounds have an overall neutral charge, so it makes sense to have 2 potassium ions to fully balance the -2 charge of the sulfate ion.
I really hope that helped deepen your understanding. And with that, we have finally reached the pair-up. Please copy down this table, including the information that's written inside the table, and include it directly under the Do Now in the classwork page that you started at the beginning of the lesson. And finalize everything with this summary slide. So write down these questions and prepare to answer them in class tomorrow. Thanks for watching. I know it was a very long and difficult lesson, but I really appreciate it, and it's going to do you good. Thanks. Bye-bye.